Hi all, thank you for tuning into my channel on ozone technology course. This is session 22B, which on cooling tower system fundamentals. The sections which I will be dealing with will be refrigeration and air conditioning, some definition on cooling systems and types of cooling towers, critical factors to consider for cooling tower treatment in cooling towers, other factors that has to be also considered, and operating performance parameters and defined specifications of water and chemicals. There are several types of cooling systems. One is when there is a cooling exclusively by passive air circulation or natural draft, just like in the fridge, or there will be a forced air draft, which is by mechanical fan or otherwise, like in the split or older single air conditioner systems. You have the counterflow of air, which means the air flows against the flow of the air. In other words, the air flows against the flow of the water, where in this case in the cooling tower it is cooling liquid or cooling water. Then there will be the cross flow, where the flow of air travels horizontally using side fans, which will push air to the water trickling down from above, and the water gets cooled. The water used for one-through cooling systems would mean that it can be only applied where there is an abundance of water, like the sea or the lake. The cold water is drawn from the source, cools the heat produced or taken to the heat exchanger, and cools the compressed refrigeration liquid, and which then goes back for the evaporation and cooling. Many big companies, factories like nuclear energy, producing organizations or companies, large-scale manufacturing of industrial plants, etc., which are sited near the ocean or lake, they use the sea or lake water for cooling in return. The water has to be treated in one way, that is, it has to be filtered of all suspended solids, organic materials, etc., and then it goes through one flow. However, in order to prevent mollusks, etc., and other things that can mollusks, etc., that can stick onto the sides of the pipes, they will add some chlorine or other forms of anti-deposits. All the equipment designed for the use will have to be made of stainless steel to withstand the harsh water or high sodium chloride solution. The next is the closed circulation loop of air cooling or water cooling. The refrigeration liquid or the water circulates in the closed loop from the compressor to the air cooling coils, then to the cooling source and back to the heat exchanger after the compressor is finished. Water may not be used. A typical example where water is not used is home refrigeration system, home and industrial air conditioner, single or split. But where water is used, the circulation fluid to cool the compressed refrigeration liquid, it will be in a closed circuit. Treatment, as it is a closed loop, the refrigeration liquid is not in contact with the cooling air, and So no treatment is required other than dust filtration of the system. If water is used in the closed circulation system, it also needs no treatment, but it might eventually cause some corrosion, so we might have to have some corrosion inhibitors to prevent eventual corrosion of the water if the water is substantially acidic or above pH 7. In an evaporative tower, the draft from the fan evaporates the water flowing out downwards, overlapping the cooling coil. The loss in heat through the evaporation of the water in the absorption matrix of the circulation water may just cool the hot refrigeration liquid. The system is less efficient than water cooling systems but require little maintenance. If the system is not used, a small volume of the water can be drained off. But also the water, while in use, may have a slight amount of treatment to prevent most likely algae infection, etc. Most of these systems are very small systems and water can be changed regularly with fresh water. Alternatively, some disinfectants can be added to prevent bacterial growth. In the wet cooling tower, this is the cooling system that is most efficient and used in very large systems, buildings, factories, power plants, large freezer rooms, and other installations. This system will be used in our ozone applications because of very high chemical usage as well as high maintenance and downtime. There are some critical factors we have to consider when we want to apply any chemicals or ozone treatment. First, we have to consider the age and the condition of the towers and pipes. Now, if the age is very old, the condition of the pipes may be corroded, etc. And obviously, use of chemicals, etc. might eventually cause leaks. And we have to take into consideration that the pipes are in good shape. The size or cooling capacity. Now the amount of water that you need to cool will be dependent on the cooling capacity. So the greater the cooling capacity, the greater cooling of the water. Next will be the feed water quality. Obviously, the feed water going to the cooling tower is also very important, that it should not be corrosive to the metals. It should not be very hard so as to deposit, scaling, etc. It should not have suspended solids which can cause erosion, corrosion in all the pipes. It should not have algae or any other vegetation that can flow through and cause clogging of the small copper pipes which are in the condenser or heat exchanger. Then the next is the water flow. The greater the water flow, the faster the heat can be transferred from the heat exchanger. We have to get it optimum because there's only a certain amount of water that can flow through, so that we have to use as little as water as possible, but at the same time we want to maximize our transfer of heat. Then that goes to the total volume of water. Now the volume of water will obviously be higher on very big cooling systems compared to the smaller systems, simply because we need that quantity of water for the transfer of heat. The factors that change in the cooling water during operations: when you start with a new tower, fresh water is normally added to the cooling tower, and they've got some specific total dissolved solids. In some areas, the water may be of very good quality and very low TDS, as low as 20 ppm, and such water is very good as a starting point. As conditioning operates and continues to operate, the heat that is transferred into the water evaporates. The water evaporates and it concentrates as the dissolved solids from the water accumulates, and this will progressively increase the TDS. There is also a decrease in volume because of evaporation, and it is necessary to add water to top up the water to maintain the same volume. And if there is a high TDS, we have to do a blow to reduce that TDS to workable, acceptable quantity. Of course, we have to add chemicals so that you have the maintenance of the quality. These chemicals will be corrosion inhibitors, algae inhibitors, bacteria biocides. Then you have scaling inhibitors, and whenever there is organic material, particularly because of organic chemicals in the biocides, there will be also foaming. So we have to have foaming chemicals or foaming inhibitors. We have to top up regularly with fresh water to maintain the optimum volume, or to blow down or remove the water that is very high TDS and top up with fresh water so that the TDS is also maintained to a certain levels. Normal water is generally corrosive. Even pH about 7, 6.5 to 7 is still classified as corrosive, and that water cannot be allowed to circulate the system because eventually it will corrode all the steel pipes. Ideally, to stop the corrosion, we have to add corrosion inhibitors. Then you have the bacterial fungal contamination of water by microorganisms from the air, which is being scrubbed by the water that falls from the top of the tower, and they have to be controlled by addition of biocides. And this is particularly necessary for one, maintenance of good tower, also for the health of the towers as well as humans. Of course, as you know, organic biocides addition would increase the TDS, frothing, so you have to have an anti-frothing or anti-foaming chemicals. We have dealt with some of these parameters in the cooling towers, but I thought it would be pertinent to just go through once again, just to recall your memory. The conductivity of the water, you call it total conductivity TC, or electric conductivity, is actually obtained by the measurement of the voltage between two electrodes and measured in microsiemens per centimeter. The greater the number of dissolved electrolytes, the higher will be the conductivity. Total dissolved solids, they are both related to conductivity because mostly the dissolved solids are electrolytes. So there is a relationship between conductivity and total dissolved solids. So total TDS is about 0.65 times the conductivity expressed in ppm. So all you need to measure either conductivity or the dissolved solids, and you can calculate the other parameter. The total dissolved solids are the amount of electrolyte solids dissolved in water. Water-soluble non-electrolytes do not conduct electricity and not measurable by this method. Then we have discussed the word blowdown. This is a process where we bleed the water. That is, we have a bleeding valve. We open the valve to allow the water to drain off, reducing the water volume, along which it carries a lot of high total dissolved solids. Then we top up to the equal volume so that the total dissolved solids will become halved. The amount of discharge of the water can be controlled by TDS or conductivity. In other words, if you want to maintain the conductivity to say 1200 or 1500, then when the conductivity or when the dissolved TDS, let's say TDS 1500, when the TDS goes above 1500, say maybe 1600, then immediately the bleeding valve will open and water will be drained out. At the same time, fresh water is topped up until the TDS is maintained about 12 to 1500. With certain parameters, performance parameters, we have to know when we do any treatment. We must know what is the total volume, total circulation volume. That depends on the cooling capacity and also where the air conditioning system is situated and the distance between the cooling tower and the AC systems. Sometimes the AC systems like the cooling heat transfer systems may be below or basement, and the cooling tower may be right on the top, maybe 10, 15, 20 floors high. So there must be enough water for the water to come down from the 20th floor of the cooling tower right down to the basement and up again from the heat transfer systems to back to the cooling tower. The turnover of cooling water is also important. The higher the turnover, the faster the transfer of heat. And the water temperature generally will be around 45 degrees coming out of the heat exchanger, and that goes onto the top of the cooling tower. And when the water comes down from the cooling tower, it sprays and cooled by the air. The temperature at the base will be approximately 35 degrees. There is about a 10-degree drop of temperature. The pH is definitely maintained between 7.5 and 8. Below 7.5 there will be corrosion. Above 8.0 there will be a lot of scaling. The TDS is generally kept below 1500 TDS. Of course, the conductivity is related to the TDS, which is about 2300 Mohs. The table here shows the parameters for operating the cooling tower water systems. The pH, they say 6.5 to 9, even though I say 7 to 8. 6.5 is pretty low, so you may have to put a corrosion inhibitor. Then the TDS of input water must be as low as possible. Less than 500 ppm means you can have a higher turnover. If it is 20 or 30 or 40, you can have a very high turnover. If it is more than a 500, then you have a very low turnover. The TDS water, 1500 ppm, has to be max. The cycles of concentration, for example, is the turnover. In this case, it may be between 5 and 8. If, for example, if the input water is only 30 ppm, then you have a turnover of 500. But if you have 500 ppm, that is only, you have only a turnover of about 3, or what you call cycles of concentration at 3. So we have to juggle and work out the optimum cycles of concentration that is dictated by the total dissolved solids of the water in the tower and the TDS of the feed water. In chemical treatment, biocides normally controlled by the supplier. Scaling inhibitors, concentration as also dictated by the supplier. Corrosion inhibitors also in ppm, but also dictated by the supplier. Corrosion levels, that they are determined, but they are specified for a particular metal, and we have to be within that corrosion levels. The type of and level of antifoam is also advised by the supplier. Flow down for the TDS is about kiloliters per day, subject to the TDS in the tower. Now we have one further parameter which is very important, that is chloride, because chloride is the biggest culprit in corrosion. So if we reduce and keep the chlorides as low as possible, then we'll have a better control system. The chloride is generally derived from the town water or municipal water because of the addition of chlorine for drinking purposes, and therefore this may be as much as 250 ppm. That includes the chloride within the water as well as added chlorine that has been converted to chloride. But the 250 ppm is the maximum we should allow in the cooling tower, above which the corrosion can be very serious. Thank you for watching my video. This is the end of session 22B. Please proceed to session 23A, which will continue with the mechanism of corrosion in cooling towers. If you are new to this channel, please refer to sessions 1 and 2 that will explain the course program, and 3 to 22 for the session's detailed program. If you like the course, please tick the like icon and subscribe icon when you will be notified as soon as further sessions are released. Thank you and have a good day.